So far we've been using the basic methods for f0 and fmin search, where we can give it a function we want to find the zero of, or a function we want to find the minimum of, and then a second argument where we give it an initial guess, and then it's going to find the zero or the minimum. However, for some functions, it's very difficult for the algorithm to find the zero or to find the minimum because it's using a non-derivative method to do so. So for these functions, it might have a tough time finding the true zero or the true minimum of the function using the default parameters. So what we can do is not only feed it those first two arguments, but we can give it a third argument when we use one of these two functions where we change the options of how it's going to be working. There's a whole list of different options we can set for how these two functions are going to operate. I'm only going to cover four kind of main functions that are going to change its behavior. The first two options we can set is what we call tall x or tall fun, or at least what Matlab calls them. And this sets the tolerances for f0 or fmin search. Basically how these two functions work, it's going to get your function closer and closer to zero or closer and closer to the minimum value, and eventually it's going to give up and say that that's close enough. So broadly, what tall x and tall fun do are adjust the tolerance for when it gives up. The smaller tall x is, the smaller tall fun is, it's going to try to get closer and closer before it says, okay, I've reached the zero or I've reached the minimum value. What tall x is going to adjust is how much of a change the x value is going to take before the algorithm stops. And tall fun is going to adjust how much of a change in the function value from iteration to iteration the algorithm is going to go through until it's below that threshold, and then it stops and says that it has your answer. We can also adjust the maximum number of iterations and the maximum number of function evaluations that f0 and fmin search go through before again it terminates and said that it has found your answer. Making our tolerances smaller or increasing the number of iterations or evaluations that f0 and fmin search go through will often result in a better answer, a better final solution as to where the zero is and where the minimum value is and what value of x causes that minimum value, but we do that at the expense of the amount of time it takes to run the function. For some easy functions, for the algorithm to go through, we're not going to notice much of a change in the time it takes to run, but for other functions that are more nonlinear or more difficult, we might see a significant increase as we lower the tolerances or raise the number of iterations. Let's go through another example where we're going to use fmin search, but in this case we're going to play with the tolerances, play with the options as we come to find our solution. In this problem, we're given 4 points, and we're trying to fit a third-order polynomial to those 4 points. Really what this is a regression problem that we're going to get to in a couple weeks here, and this is the basic premise of how a regression is going to work. So we're going to kind of see what's behind the scenes now, and then later we'll be able to use tools that will automate the process that we're going through. This problem is trickier than the ones that we've been looking at previously, so let's see how we can start to arrive at a solution for this problem. We have to come up with a method that we want to use and then actually implement it in the Matlab code. So first, we know that the function is going to pass through these 4 points. So let's start by just plotting these 4 points. And I can use a scatter plot for this. So I know that my x values are going to be -2, 0, +2, and 4. And then the corresponding y values will be -20, 4, 68, and 508. I'll make big markers, and I'm going to make these red squares so that we can see them. And let me run this. Alright, so these are the 4 points that this cubic polynomial is going to have to fit through. See a little bit more with the grid. Alright, so we need to find the cubic polynomial that best fits these 4 points, and then that cubic polynomial will also be able to estimate the points in between. So the premise here is we're choosing these 4 coefficients, a, b, c, and d, in our cubic polynomial that's going to make the curve that if we have a given value of x, it's going to be able to find the appropriate value of y. So just as a demonstration of what we're really going to look for here is we're going to have x values for the purposes of this from -2 to 4. And I'll put 100 points in between. And again, we are coming up with a function where given an x value, we're going to be able to compute the appropriate y value. And I'll call this capital X so that we don't confuse it later. So the way that y is going to be computed is it's going to take some a value times the x value cubed plus b times the x value squared, and so on. So one way that we could write this is that it's going to be a times x cubed, I'll do this as a vector, plus b times x squared plus c times x plus d. And what I could do is I can set, here I'm just going to set arbitrary values for a, b, c, and d. And I'll be able to see what this looks like. And running this, let me suppress this. So superimposed on the scatter plot, I'm going to put, just as a demonstration, what if a, b, c, and d are all 1? So if I plot on top of those points, this is if all of my coefficients are 1, and we see that the black line here is going to be that cubic polynomial when a, b, c, and d are all 1. And we see that it doesn't go through these 4 points here. Now manually I could go through and start playing around with these numbers. So again, I'm just kind of arbitrarily picking values. Here we see that really by chance it does go through the second point, but it doesn't go through the other points. And if I keep adjusting, I see that actually with that guess I'm not too far off actually, but it's going to take us, if we're doing this manually, many attempts, probably an infinite number of attempts if we're just randomly guessing, for the cubic polynomial to actually go through all 4 of those points. So what we want to do is have an automated or kind of more intelligent process for picking these four values a, b, c, and d. And what we can use for that is an fmin search to automate this entire process for us. So actually, first thing I'm going to do is, because the x's are going to be given to me, it's a, b, c, d that I'm going to be finding the values for. I want to convert this into using a vector a that will have 4 components to it. And we'll see why in a minute this is going to be superior once we get to using fmin search. So what I can do here is I can now redefine this a vector to have 4 components, and they correspond to or map to my original a, b, c, and d. So if I run this, I get exactly the same thing I just had, but now I'm using those coefficients in one vector that I'm calling a, rather than 4 scalar quantities. So what I want to do here is I want to pick the values in this vector a, in this case 4 values. They're going to make the cubic polynomial best go through those 4 points. So I have to think about here, what do I want, if I'm going to use fmin search, what am I actually minimizing? So let me make a function. I'm going to do this as an M file rather than inline because it's going to be a little bit more complicated here. So I'm going to make a function that's going to output what I'll call error. And I will call this L02EX1. I'm going to have it take the vector a. These are the coefficients that go into my cubic polynomial. And save it with the same name. So again, we need to create a function that we're trying to minimize. So again, we want to think about, if we have this plot here, what are we actually trying to minimize? There are different approaches for finding this fit, but what we can do, let me change these back to other values so we can see kind of more stark a difference here. One way we could think about this is that we want to minimize the total distance between this black line and these 4 points, or what we want to do is minimize what we call the error, which is the distance between where the black line is and where the red square is. So for example, here we see we have a little bit of a difference at this first plot point. The second plot point is almost directly on. We have a little bit of difference at the third plot point. At the fourth plot point, we're actually way off here. So what we can do is if we add up these 4 distances, when those 4 distances add up to 0 or add up to a very small number, that means that the line is going to pass through all 4 of those points pretty much exactly. What we can do is for a given value of a, I can then compute what are those 4 y values that the curve is going to have. So I can set up this vector x, which is going to be, again, those given x values that we had, -2, 0, 2, and 4. And I can compute from here the y values of the cubic polynomial at those 4 points. And to do that, it's going to be, I can do a, which is a1 here, or a of 1 here, times x cubed, plus a2, which corresponds to b, times x squared, plus a3, which was originally called c, times x to the first power, plus d, which I denote as a4. Alright, so what this is going to do is going to compute the value of y at these 4 values. So again, let's just look at how this is working. If I have this vector a, which I already have here, I can't run the function yet, but I can run just this line. So if I denote this as x, if I calculate this, I get my 4 values of y that correspond to those 4 values of x. And this matches, if I go back here, this matches the values of y not everywhere, but only at those 4 points, -2, 0, 2, and 4. So these 4 points are what I'm trying to match with the black squares. Right, so I have the values of y, but again, what am I trying to minimize here is the distance between these 4 values of y and the given values of y that I had. So what I can do to start to compute the error is, if I know the distance between my estimate from the cubic polynomial and the given values, again, when that total distance reaches 0, that's what I'm looking for here. So what I can start with is I can take these 4 values of y and subtract from there the known values of y that I have. So again, what we see here is this is the total error that we have, or our distance between the polynomial and the given values. So we see we're only 16 away, we're only 2 away, 12 away, and then we're 206 away. Ideally, what we have here is that if all of those are 0, that means that the points coincide. However, for fmin search to work, it can't minimize 4 things. Fmin search can change a vector of values, but it's evaluating the thing it's trying to minimize can only be a scalar quantity. And right now what we have is a vector quantity. So I can't just minimize error because it's a vector right now. I need some scalar that I can minimize instead. So what I can do is I'm going to use the norm function here. And basically what the norm function is, it's basically like taking, using Pythagorean theorem. So what it's going to do is, if I take the norm of a vector, I'm taking the square root of the sum of the squares. So if I take the norm of error, so again, just to recap, I have error here is this vector. If I take the norm of the error, I'm taking the square root of 16 squared plus 2 squared plus 12 squared plus 206 squared. I get 206 as the value. So, but you see here, it's a scalar quantity. When this goes down to 0, that means that my total error is 0. So I'm going to redefine error here as the norm of how I was previously calculating error. And I will suppress this. Right, so again, what I'm doing here is I'm just measuring what's my cubic polynomial at those 4 points. I'm then computing the distance between the known values, these red squares, and where the black line is at those 4 points. When that total error, as I'm defining it here, reaches 0, that means that the black line coincides exactly with the red squares. And that's what I'm trying to do here when I'm doing my fit. So going back to my main code, from here, I'm going to get rid of this definition for the moment. So instead of just arbitrarily choosing a value of a, I'm going to let fmin search do that for me. So I want to do an fmin search on the value of a on my function LO2 EX1 of a. Right, so again, going back to our function here, it only takes one argument, a, and it gives me one output, which is the error, or ERR. So that's ERR is what it's going to try to get to 0 by adjusting the values of a. In this case, I have to give it then the initial guess. Going back to my function, a should have 4 parts to it, a 1, 2, 3, and 4. So for my initial guess, I have to give it 4 values in that vector. And I won't use it with options for right now, just so that we can see how it works. Right, so if I just run this line, let me start over here. Right, so those are my original plot points. fmin search, it says that my values of a that minimize my function are 7, 5, -6, and 4. So I want to save those. And I'll also save the value of the function. Right, so a is now saved as a 4-element vector, and the minimum value of my function is pretty small, 4 times 10 to the -5. If I go through and run the whole thing, and now I plot it with these specific values of a, we see that the cubic curve that it came up with here is 7x cubed plus 5x squared minus 6x plus 4. And we see that graphically what's happening is that at those 4 points, it coincides pretty much exactly. So this would be the coefficients I would use that would be a regression for these 4 points. Now I can extend this out a little bit here because I can give some options to how fmin search is going to work. So I'm going to use what's called Optima Set, and this goes back to what I was talking about on the previous slide. This is where I can set the values for tall x and tall fun, etc. So actually, let me hold off on this for the moment. I'll come back to that in a second here. fmin search actually can give me 4 outputs. I usually only use the first 2 though. But I'm going to see what are the other outputs that it normally would give me. So I'm going to rerun this, now taking flag and output, and explain what those do in a minute. So if we go in our command window, we have that a vector. We have the minimum value of the function that it determined. We have a flag equal to 1, which I'll talk about in a second. And we have this text from outp that I called. In this case, outp gives us information about how the function ran and what options it was using. So it said that it terminated after 271 iterations, 457 functions, which algorithm it used. This is a non-gradient or a non-derivative method. But what we're going to look at here is the reason why the optimization terminated. So it said here that the change in x was less than the default value of tall x was 1 times 10 to the -4th. So again, that change in this case a, the change in the coefficients was small enough that it just stopped running. What I can do is actually change that. Before I get to there, the flag that comes out, 1 means that it successfully terminated the operation, which means it was satisfied and it gave an answer. If we get a 0 for the flag, that means that something went wrong and the answer it gave us didn't meet one of the criteria for being satisfied with the answer. Let me go up to these options now. So we see here that it terminated because tall x was less than 1 times 10 to the -4. So what I can do here is I can, instead of 1 times 10 to the -4, I can make it smaller. So I'm going to make it so it doesn't terminate until the change in x is 1 times 10 to the -6. And what I have to do to tell it that I want not the default options is add a 3rd argument to fmin search. I have the function, my guess, and now my options that I'm running. So if I rerun this whole cell, we see that even with the default options, we were getting pretty good results. But here, our fmin is actually smaller. It's 2 orders of magnitude smaller, meaning that the error is even less, although we see to the number of digits it's displaying that a has not changed. But we see here with the output text that now it terminated, again, because the tall x was less than 10 to the -6. So I can keep going down with this value, although we're not going to, in this example, see really an appreciable difference. I can also adjust the value of tall fun. Let me rerun this with tall x and tall fun. Keep going. So I can actually go pretty small on this. And we see that if the tall x is really, really small, again, that fmin is even smaller than it was before. We're now 7 orders of magnitude smaller. But now if we see the output text, it didn't stop because tall x was exceeded. It stopped because max fun evals was exceeded. So what we can do is, if we were to want to go even finer on this, I could increase the value of max fun evals. I'll try 1 million. Right, so now in the out p, it gives me that the max iter was exceeded, so I can up that so it does more iterations before it gives up. Again, just for this, I'll say 1 million. So you see it's taking a while for it to run now because I've kind of put a very low tolerance on and I'm letting it run 1 million times before it's going to give up. And it's completed. And it says that now it exceeded max fun evaluations, but that did take quite a while for it to run. And we see actually the minimum value found is not much better than it was before. So to recap this problem, again, we had to kind of interpret what we were trying to look for and then define a function that we did want to minimize. So in this case, we had to come up with a function to minimize. So I used the total distance, or really the total positive distance between where my cubic polynomial was and where these 4 plot points were. I made a function that would calculate what that total error was. And then I put it into an fmin search so that I could find what were the coefficient values that were going to minimize that total error between my cubic curve and those 4 points. And then lastly, we tweaked a little bit with the options here to make the tolerances smaller and to let go from more iterations. So again, running it one more time, we see, actually it took a while, let me run this with fewer function evaluations, fewer iterations, just so it works a little bit faster. We see that this is the curve, and we see that it pretty much exactly goes through those 4 points that were specified.